Welcome to the Rich Report, a podcast with news and information on high performance computing. Today, my guest is from MBA Sciences Incorporated. We have Minesh Amin, and Amesh is here to tell us about SPM Python. So, Minesh, welcome to the show today.
Thank you. Thank you, Rich.
Well, I want to welcome you back. We talked a while back here with some podcast information, but I understand you've got some new things to tell us about, and even a speaking gig coming up at SC11.
Yes, we have supercomputing. There's a Python HPC workshop on Friday, November 18th. Yeah, we are going to roll out two specific kinds of capabilities at both of those talks. Details we can cover next.
Okay. Well, I have your slides up here. Why don't we go through that? I'll follow along. Just tell me when you're changing slides.
Okay, so we go on to the second slide, and basically we have three announcements. One is we got our second patent issued on November 1st. The first one was issued back in April of this year. And the second announcement has to do with the integration. SPM.Python going forward will be able to integrate with OpenMPI, and the details of which we are going to cover next week at Supercomputing Conference, November 18th. And the third capability has to do with advanced parallel primitives for data and compute-intensive workloads. And that will be covered. That's a talk that's scheduled for December 6th at Stanford University. And the theme across the board is here we have, with SPM.Python, it's a single, rich, easy-to-relate to environment for exploring parallelism across the breadth and depth of the parallel landscape. So unlike competitive solutions where they're either highly focused or single kind of a single framework or library-based, this is a rich environment made up of a suite of parallel primitives that allow people to express parallelism across breadth and depth. Some of their details we'll be covering today. So on to the next slide. So what is the anatomy of the U.S. patents? What's the simplest way to think of the patents is the following. Think of the serial session as depicted on the left-hand side. You have a typical serial session in Python or any tool, doesn't really matter. And we are executing 4 commands here, A, B, C, D. And typically they tend to be CPU intensive, then IO intensive, then CPU intensive, and IO intensive. But in other words, we don't even think about these things. We just execute them one after the other. And that's what we are able to do in a serial session. Take the same resource, in this case a single compute resource, and use that resource to solve problems that may be compute intensive or IO intensive. So it seems rather natural, right? And what the patents allow us to do for the first time, unlike any other competitive solution, is that we can now come up with a parallel session that has a look and feel kind of similar to the serial session. Namely, we can invoke multiple parallel commands, one after the other, using the same resources in completely different ways. So, for example, command A in the serial mode may be solving some problem, but whose parallel version requires MapReduce. Command B could be solving some problem having to do with satisfiability problem, but whose parallel version requires probabilistic data structures. Command C could be some make job, compiling of some jobs, compiling of some source code, but whose parallel version requires the processing of a DAG. So what this allows us, and that's the guts of the patent, is given a collection of resources, how do we use the same resources to exploit different forms of parallelism within the same session? And a corollary to that is, if you can think of this, which seems like a rather natural if you come from the serial world, a corollary to that is the ability to use the same environment to express different forms of parallelism across sessions. Here, A, B, C, D are in one session. They don't have to be one session. They can be in 4 different sessions. So that's the gist of the U.S. patents that were issued. How do we pull this thing off? And so going on to the 4th slide. So armed with the patents, what does the SPM technology look like, the core technology? It's basically, we have the core kernel that exposes various suite of parallel primitives. So unlike other approaches, Typically, parallel-enabling technologies can be classified in one of three ways. You have the library-based approach. Examples include OpenMPI, OpenMP, the CUDAs of the world. They hug the respective hardware resources. The users have maximum flexibility, but also maximum headaches, and they also have to deal with fault tolerance. The second kind of parallel-enabling technologies are framework-based. They take the opposite approach, where they focus on a particular class of problems, simplify that, and expect the developer to provide certain callbacks. So, for example, in MapReduce framework, the MapReduce framework takes care of fault tolerance, but it expects the developer to provide map and reduce functionality. With SPM.Python, that's the third approach by which to exploit parallelism, and that is not to think in terms of libraries or frameworks, but to think in terms of parallel primitives. And the reason this is important is because now we can, if we have 10 different forms of parallelism, we don't need to deal with 10 different frameworks. We don't need to deal with 10 different libraries. We're just dealing with one environment that has 10 different primitives that are available to us. And we pick and choose depending on our needs. So that's what the core technology allows us to do. So the key point here is, again, parallelism is expressed using appropriate parallel primitives and not frameworks. That's the game changer. Getting to the fifth slide. So as I mentioned, we're going to describe at the Supercomputing Conference our integration with OpenMPI. So what's the problem with OpenMPI? Well, typically what happens is it's a very fast thing. It's a very efficient way of exploiting certain kinds of parallelism, fine-grained typically. And what I've shown here with the baseline is this is typically how you invoke it. You have an MPI run, kind of a wrapper that invokes the application in question. And the problem with this OpenMPI applications is it lacks one fundamental property of any parallel application must have, and that is it's not fault tolerant. So it could hang, it could deadlock, it could have all kinds of nasty behaviors. Now you may wonder what's the big deal? Well, if you run this OpenMPI application that does not have support for fault tolerance on a public cloud, and it hangs, the public cloud is going to charge us per minute or per hour, even though nothing useful has been done. And so that's the biggest problem with OpenMPI applications. Consider even legacy OpenMPI applications. The authors are long gone. The code is written in Fortran. It does a useful job, but sometimes it hangs. And again, you're running it for doing all oil simulation, oil extraction simulation, all kinds of things. Nobody wants to touch the code, but everybody recognizes that when you run it on a public cloud, huge bills are incurred while doing nothing useful. And so with SPM.Python now, what we can do is launch the same application, in this case, Hello World, using SPM.Python, but in a way where Hello World becomes fault tolerant all of a sudden, without changing the code and without having to recompile anything. And the details of how we went about doing this will be covered at the Supercomputing Conference, the Python HPC workshop on Friday the 18th. But so this is what it allows now. Thanks to SPM.Python's built-in primitives and its robust notion of fault tolerance, we now all of a sudden, for the first time, have some other form of parallelism kind of inheriting this rather critical property. So now we go from a baseline flow to one which is a drop-in replacement, but it has this additional requirement saying you have to make sure this thing finishes in 20 seconds. And so all of a sudden, it basically concludes within 20 seconds. And there's no way it can extend past 20 seconds. And there are a whole lot of other deadlock situations that it detects also. So that's the integration with OpenMPI. And finally, with on slide 6, building on this theme of the fact that we have a single environment, a rich environment made up of primitives, we'll be building on this by describing advanced primitives for big data and graphs at Stanford University. Again, the common theme here is, notice I talked about leveraging OpenMPI applications. I've talked about describing graphs and data. They are fundamentally different forms of parallelism, and yet they can all be expressed using one infrastructure, in this case, SPM.Python, thanks to these primitives, which in turn are possible thanks to the patented technology, which really finally leads me to the conclusion, which is, well, we mentioned this in April, but this is truly the case now. Now we have, for the first time, this idea of exploiting parallelism across servers, cores, and GPUs is possible. not just for toy programs or embarrassing easy form of parallelism, but for really sophisticated stuff. Data flows, fine-grained, coarse-grained, involving graphs, all kinds of things are now very easily possible. I've included 2 links to our talk, Supercomputing Conference and the Stanford workshop. And our next release, which is at the end of November, will include data support for OpenMPI. But otherwise, looking forward to, viewers can come by the website, try out the trial edition, and if you're interested for OpenMPI support, come by in November. And otherwise, that's it.
Great, Minesh. It seems like you've made a big step here. We were talking before we turned on the recorder about the value proposition for a small company like yours and coming out. What's changed since we last talked?
What has changed is prior to our last talk, the primitives that were made available, there were other ways of doing things. Like you did not have to use our primitives, you could use MapReduce to solve the problem, or you could have scripts that are authored or hacked by the individual developers to parallel certain things. So the only thing that it brought to the table with the prior version of SPM.Python was convenience and fault tolerance. And now there are many situations where, even though I can say that fault tolerance is very important and you pay a price for it, people don't mind paying a price for it if it's not a critical thing. But now with this advanced second generation of primitives that are augmented on top of whatever we had before, now we're talking about solving problems that are so compute intensive, that involve so much data, that it really makes a difference. Like, for example, processing of logs. If you use a MapReduce way of solving the problem, you could require 1,000 machines. But you use our approach, you will get away with only 25. That's a 40x reduction. And the reason it's possible is because the primitives are so advanced and it's so easy to relate to. Same thing with graphs. Today, there are ways by which there are various open source capabilities, and including, I think even IBM has a capability that allows people to process graphs. They either tend to be open source, and therefore they lack fault tolerance, or they have separate standalone frameworks. So you have to download them, you have to install them, the IT guys have to get involved. And you may have other infrastructure that allows you to express other kinds of forms of parallelism. The point here is, for the first time, we now have very powerful forms of parallelism. Data flows, fine-grained parallelism, MapReduce-like infrastructure for processing huge logs, all that easily accessible from one infrastructure, not from N libraries or N frameworks. That's the biggest difference. And in a way where performance, we have gone out of our way not to publicize the numbers, because there's no point. We are happy with whatever numbers the customers report. There's no point second guessing their numbers. All we are confident about is the numbers are incredibly good, and they have to be good because it's all really, really efficient. So now the value proposition is, we're talking of not toy programs, we're talking of huge problems that take hours to days to get executed. And to do that all in fault-tolerant manner, and to do it with the least amount of effort. That's the biggest change.
So, Minesh, talking about fault tolerance, right? A lot of users for this kind of thing might be scientists or data scientists, but fault tolerant, they aren't writing typically enterprise apps. It's not something they're trained in. It's not something that they typically have to worry about. But with big data, it sounds like a problem run like this could take days. Suddenly, fault tolerance becomes very important, doesn't it?
Yes, especially, first of all, fault tolerance is always important the minute you start using public clouds.
Yeah.
The minute you use public cloud, that cost that is associated with you using a public cloud is now staring at you in the face. You don't have to go through IT or some other manager to figure out what the cost of that nightly run was. Right? So anybody now has very easy access to the actual cost of running that individual experiment. Previously, if it was part of the IT infrastructure, it's kind of, who knows what the amortized cost equations are and whatnot. Here, it's very explicit. You ran the experiment yesterday overnight, 8 hours, this is the bill.
And in that context, if fault tolerance is lacking, for the first time, the value proposition is just staring you in the face. There's no point in me even providing you with the data. You see for yourself. And with that, the question then becomes, if fault tolerance is lacking, then the question is, you are paying a penalty when your solution deadlocks. And it's a question of when and not if. And the more resources you use, the bigger the penalty. And you throw in GPUs whose hourly rates are even higher, and you pay even a bigger penalty. So for the first time, this is like literally standing at you in the face. So when we compute our value proposition, we go first by the failure rate. If you're running 10 experiments, of which 4 of them fail, what is the average time that you waste because those 4 of them deadlocked or something like that? What is the hourly rate from Amazon? Amortizes, and you see that whatever our licensing model is comes out far ahead of whatever price you are paying for just hanging your solution. You see what I'm saying?
Yeah.
And this is assuming that you are not even changing your code, like in case of OpenMPI. So the good thing about public cloud from a small startup point of view is that the penalty for not doing things, not having fault tolerance is now very easy to compute. The customers can see it for themselves, and we can justify whatever our licensing schemes are relative to whatever price they are paying. That's the biggest advantage.
Yeah. So Minesh, kind of a wrap-up question here. You know, if our listeners they're intrigued and your release is coming out right after Thanksgiving on November 30, how do they get their hands on this and try it out?
Right now, it's immediately available, so they can try out. Of course, it doesn't have the OpenMPI component in it, but the trial edition has this. And on November 30th, they can download it from the website, or in the meantime, they can email me.
Well, Minesh, I want to thank you once again for coming on the show today. Okay, folks, that's it for the Rich Report. Stay tuned for more news and information on high-performance computing.